Here's another fun example. A rational function. We haven't seen that yet. Let's talk about local and global extrema all in one. All right, so where do we begin? How about domain? Let's talk about the domain. Since it's a rational function, we know anything that makes the denominator equal to 0 is excluded from the domain. So if I say x squared plus 1 equals 0, and I solve that, what happens? I'm saying some number squared is negative 1, or x is plus or minus square root of negative 1, which is not a real number. Which means there is no real number that would make the denominator 0. So just for making a note here, let's say that anytime I have x squared plus some positive number is always going to be greater than 0. Okay? So what that means is then that the domain is all real numbers. Okay? So even though it's a rational function, the domain is all real numbers. Okay? All right. So what do we want to do? Let's find global extrema. Okay? So what we need are critical points. So first thing I'm going to do is find the critical points. Which means first derivative. Here we go. What rule are we using? We are using the quotient rule. It is a quotient. All right. Good review of derivative rules. Quotient rule says derivative of the top, which is derivative of x, is 1, times the bottom, minus the top times the derivative of the bottom, all over the bottom function squared. Okay? Now, in the good old days, we didn't have to simplify, but we really need to simplify now because we have to see what makes it equal to 0. So if I fix the top up, I end up with x squared plus 1 minus 2x squared. And you could stop here if you wanted. We could also fix the top a little bit more and combine like terms. That's a 1x squared and a negative 2x squared, which leaves me with, what? Negative 1x squared plus 1 all over x squared plus 1 squared. Okay, so if you recall, when we want to set that equal to 0. Okay, and that basically is a rational expression is only 0 when the top is 0. So set the numerator equal to 0 to find that. Because remember, this is always positive. It's always positive. And whatever makes it 0 would be not in the domain anyway. So it's always positive because of the square. Okay? So to figure out what makes negative x squared plus 1 equal to 0, we solve. We end up with x squared equals 1. So x equals plus or minus 1. Okay? So these are my critical points. My critical points are x equals 1 and x equals negative 1. All right, so if we want to know, since my domain is all real numbers, then I don't know what's happening at those critical points. Okay, so let's talk about those being, if those are local extrema first, and then we'll decide if they are global extrema. So let's do the first derivative test to decide if we have local max or min at each of those. Okay, so number line, I've got negative 1, I've got positive 1. I am going to substitute into the first derivative and find out what's happening on the graph of my function. Okay, so let's choose a test point. So I'm going to test -2 and 0 and +2. Okay, so we're testing those in the first derivative, which means up here. Okay, now it's not going to be terrible because the bottom's always positive, so is -2 going to make the top positive or negative? Okay, so you can do that testing. Pause the video if you need to. When I put in 0, I get 1 on top and I get a positive number on bottom. So that's going to be positive. When I put in 2, I get the same thing as -2. I get a negative. So that tells me then that my function is decreasing, then it's increasing, then it's decreasing. So that means then that at here at -1, I have a local min, and at 1, I have a local max. Okay? Okay, so how do I know if that local max and local min are global max or min? Well, here is where we have to kind of rely on the graph or what we know about rational functions. So let's think about this for a second. We've got -1 and +1. What's happening at those points? Let's just substitute those critical points in to the function. And when I plug those into my function, I get at -1, I get -1/2. So I've got this point here. And at +1, I get +1/2. Okay, so here are those points on the graph, or those are my critical points. So what about x-intercepts? Okay, how do we find the x-intercept? Basically, where does my function, let's see if this graph crosses the x-axis. Where does my function equal 0? Okay, remember, that's where the numerator equals 0. So x equals 0 is going to be my x-intercept. Okay, so I have this point. Okay, now what's happening far out to the end? So somehow my graph is doing this. Okay, but recall, let me write my function down here again. Sorry. Okay, so whatever makes the numerator equal to 0 results in my x-intercept. Okay. And that's my only x-intercept. So basically, as I go farther out here to the right, my function is never going to cross the x-axis. Okay, so that means even out here, it's never going to cross over. So the graph is going to be strictly above or below the x-axis. And how can we solidify that? Remember our test for horizontal asymptotes back in algebra? If the degree of the top is less than the degree of the bottom, the horizontal asymptote is the line y equals 0. So we're saying that basically my graph will not cross my end behavior. It won't cross far to the left and far to the right. So I can tell from the graph that this is also a global max. And this is a global min, which we looked at that graph in one of our examples at the beginning of section 4.3. Done.